guys, today we're going to do section 3-4 linear programming. So we will be able to solve problems using linear programming. The big idea. Some real-world problems involve multiple linear relationships. Linear programming accounts for all of these linear relationships and gives the solution to the problem. So, linear programming is finding a maximum or a minimum value of some quantity given some constraints or limits. The constraints or the limits in the linear programming situation form a system of inequalities, like the one at the bottom of the page. The graph of the system of inequalities is the feasible region. So it contains all the points that satisfies all of the constraints or all of the limits that were given. The quantity you are trying to maximize or minimize is modeled with an objective function. Often this quantity is cost or profit because we want to minimize our cost and maximize our profit. Suppose the objective function in the equation below is c is equal to 2x plus y. Graphs of the objective function for various values of c are parallel lines. Lines closer to the origin represent smaller values of c. So the graph of the equations 7 is equal to 2x plus y and 17 is equal to 2x plus y intersect the feasible region at these 2 points 2, 3, and 7, 3. These vertices of the feasible region represent the least and greatest values for the objective function. So we have our minimum and we have our maximum. So a key concept, if there is a minimum or a maximum of the linear objective function, it occurs at one or more of the vertices of the feasible region. So we can solve a problem using linear programming by testing in the objective function all of the vertices of the feasible region. Once we know which one gives us the highest value or the lowest value, will give us our vertice. So, testing vertices. At what point in the feasible region maximizes p for the objective function? P is equal to 2x plus y. So we have our constraints to the right. We need to graph, for step 1, we need to graph each one of these inequalities. So please go ahead and graph every one of these inequalities. After I graphed all of my inequalities, my graph kind of looks like a big colorful mess. However, I need to find my feasible region, which is where all of the inequalities are satisfied, which is this section here. Since this is the important section to me, I'm going to go ahead and erase everything else on the outside of my graph so I'm not as confused. So my coordinates are 0, 0, 0, 2.5, 3, 1, and 2, 0. I now need to take each of these points and evaluate them at p. So I'm going to plug in my x and y values to find out what p would be. Go ahead and do that now. Once you find all of your p-values, the vertex that gives us the maximum point is 2, 1 with a p-value of 7. So maximizes P would be 3, 1. C. Problem 2, using linear programming to maximize profit. You were screen printing t-shirts and sweatshirts to sell at the Polk County Blues Festival and are working with the following constraints. You have at most 20 hours to make shirts. You want to spend no more than $600 on supplies. You want to have at least 50 items to sell. How many t-shirts and how many sweatshirts should you make to maximize your profit? How much is the maximum profit? So we know that one color t-shirt takes 10 minutes to make and supplies cost $4, where we have a profit of $6. A 3-color sweatshirt takes 30 minutes to make, supplies cost $20, and our profit is $20. So what we're going to do is write all of our constraints and prices all into a table. So our minutes for a t-shirt, for each t-shirt is 10 minutes. So for X amount of t-shirts, it's 10X. Sweatshirts is 30 minutes per sweatshirt, so 30Y. Then we have a total of 20 hours. Since we're in minutes and in hours, we need to convert that 20 hours into minutes to make it 1,200 minutes. Then our next constraint is we don't want to spend more than $600 on supplies. So our cost, $4 for the cost of a t-shirt, $20 for the cost of a sweatshirt. And that total has to be less than or equal to $600. Sorry, in the first time, we can't spend more than 20 hours, so it has to be less than or equal to as well. Then we have profit. The profit for a t-shirt is $6. The profit for a sweatshirt is $20. So our t-shirt plus our sweatshirts is equal to our t-shirts plus our sweatshirts. Then the number, we want to sell at least 50 items. So if we want to sell at least 50 items, the number of t-shirts plus the number of sweatshirts needs to be greater than or equal to 50. We also know that the number of t-shirts needs to be positive and the number of sweatshirts needs to be positive. So X is greater than or equal to 0 and Y is greater than or equal to 0. Now that we organized all of our information, we know that we need to graph all of our inequalities. So take a second and graph those inequalities. To make this neater for us, I went on Desmos.com to graph the inequalities. So 10x plus 30y is less than or equal to 1,200 is this red inequality. Then I have x plus y is greater than or equal to 50. Then I have 4x plus 20y is less than or equal to 600. Then I know that the amount of t-shirts needs to be greater than 0 and the amount of sweatshirts needs to be greater than 0. So instead of having this whole, the x is greater than 0 and y is greater than 0, I'm going to take those out because we just know that it has to be in the first quadrant. So we need to find our vertices, which are labeled here, to then find what will maximize our profit. So I'm going to screenshot the graph for us. And now we need to plug in our vertices. So go ahead and do that on your own right now. After we get all of our p-values, we find that our highest p-value is equal to 750. which would mean X is equal to 75, Y is equal to 15. So we would maximize our profit by selling 75 t-shirts and 15 sweatshirts. That's all.